Here is an improper integral that, if it's possible to do so, I need to determine what the value of this integral is. You know, it could not exist, I suppose. It's improper, of course, because of the minus infinity and the infinity. And also, there's something special about it. Because it has both minus infinity and infinity, I have to split this integral into two integrals according to the techniques given in the learning module. There are going to be actually two limits that we do. So once I do that, I can split this into two integrals. The integral from minus infinity to 0 of the integrand plus the integral from 0 to positive infinity of that same function. And forgive me, there's a little typo here. Make sure that that's x to the 6th in your work. So the 0 does not matter. I get to pick it. And you could pick 1 or 2 if you like. I pick 0 because I feel like it's easiest. So now I'm going to rewrite my improper integrals as limits. I have the limit as t goes to minus infinity of this integral, plus the limit as s goes to positive infinity of the integrand. So for clarity, I have picked two different letters here for the limits, s and t. Mathematically, it would be fine for you to use t both times. I really don't care. I chose to use two different letters. Okay, now I have my two limits. And what comes next is I really need an antiderivative. So I'm going to go off to the side with this and figure out what the antiderivative is. And I'm going to execute a substitution. We're going to set u equals x cubed and then du equals 3x squared dx. And what that means is that the x squared dx here gets turned into 1/3 du. And that x to the 6th power is actually going to turn into u squared. Okay? So now, what I'm going to do here is something sneaky. I am going to factor out that 1/3. Well, that's not sneaky. But I'm actually also going to factor out a 4 from the denominator. And that is going to turn the denominator into 1 plus the quantity u over 2 squared. Why would I do that? Because the way calculus was drilled into my brain years ago, if you see something that looks like 1 over 1 plus things squared, my brain is shouting at me, arctan. That's supposed to be arctan. So I saw this and I wanted to make it look like something where I could use the arctan function. And indeed, this antiderivative is going to be 1 over 12 times 2 times arctan of u over 2 plus c. So now I have an antiderivative. I go back to the main problem and I replace both of these integrals with their antiderivatives with these evaluation bars, right? And so what I'm going to do next is actually execute the evaluations. I'm actually going to work inside of these two sets of brackets. And remember that arctan of 0 is 0. That's why there's only going to be one term for each of these. I have minus 1 over 6 arctan t cubed over 2. And on the second limit, I have 1 over 6 times the arctan of s cubed over 2. So do you remember that the arctan function has two horizontal asymptotes? So these limits actually exist, which is completely awesome. You can substitute negative pi over 2 and pi over 2 for those limits. Reducing and simplifying, you get a pi over 6 as your final answer. So this integral totally exists. Or in the new parlance, it converges. I do want to say that this thing that I've written very rapidly and messily is a second totally valid technique for you to use for getting this improper integral done. You could do it with a single limit where you have negative t here and t here. It actually might be shorter and easier this way. You're still going to replace this with the arctan function, that's the antiderivative. And then when you evaluate, you'll get two terms with t in that you'll be doing a limit to. But you should still get that very same answer of pi over 6. So I do want to mention that this will work perfectly well for you.